So once again, good evening. Today we have a talk by Professor Kajari Mazumdar. She is currently a professor at TIFR Mumbai in the Department of High Energy Physics. She obtained her PhD in 1992 from TIFR itself and subsequently joined TIFR as a faculty member. She has been participating in the CMS experiment. Of course, you all know it's an international collaborative experiment at Large Hadron Collider, LHC at CERN. Ever since it was the Indian collaboration has been formed and started working on the detector R&D and so on. So this was way back in 1996. Over these past almost 25 years, she has played very significant roles in several aspects of this experiment. She's the leader of the CMS group at the TIFR and is also responsible for the International Grid Computing Facility for CMS, which is hosted by TIFR on behalf of India. She's coordinator of India CMS collaboration, in fact, during two terms, one initially during 2011-13 and also 2015-17. Further, she has been holding several responsible positions in the CMS international collaboration, including being a member of the CMS management board. As I said, today she's going to talk on the first decade of LHC over and two more to go, in which she's going to talk about the large-scale detectors which are used in the field of high energy physics, and in particular, of course, at the collider facilities. So with these few lines of introduction, I now request Professor Kajari Mazumdar to take up and deliver her lecture.
Okay, you can hear me well.
Yes.
So thank you, Satya, for the kind introduction. I was happy when you told me to come and give a lecture in this series, but I wondered that what can I talk, because I don't know anything about neutrino, though we do encounter neutrinos so much even in the LHC context, but
Yes.
about the experiment ideas. But you explained that, okay, it could be different type. So I have kept the lecture meant for at a very low level for like stories. But seeing experts like Rajaji, I am a bit feeling a bit odd. But anyway, let me get started. So as the title says, first decade of LHC is over. We are actually in a celebration mood that already LHC ran successfully for 10 years. And we also know that LHC is going to run for a long time, at least for 2 more decades. So the audience here, I think, mostly are much junior to me. So this LHC is actually a facility for you to jump into this project and enjoy this. So as you can imagine, that as Dr. Satya has mentioned, that I have been involved in this LHC project for a long time. So I am really passionate about it. So I am always excited about it. Let's get started. And I can only mention only few aspects of this LHC. Let's see how it goes. Okay. So see, on slide 2, I just start with these Nobel Prizes in physics. As you all know, that Nobel Prizes are typically given every year, and physics, of course, is one of them, except for a few years when no Nobel Prizes were given. I think on several occasions, for 4 or 5 occasions. So among 113 total Nobel Prizes given in physics, 30% of them are directly in the fields of elementary particles or high energy physics. So with every development of technology, puzzling discoveries were made, which in turn led to the theoretical developments. And surely deserving people went away with the Nobel Prize. Of course, there are many cases, today also we will see that several people didn't get it, but that always happens with the prizes or the recognitions. So first prize was given in 1901 to William Röntgen for the discovery of X-rays. And of course, the Nobel citation said that for the service to the humankind, etc., etc. But I would say that it recognized the importance of doing thorough experiments and interpreting the results correctly. That was the importance of this prize. So today we shall talk about one of the most anticipated discoveries in physics, which led to the Physics Nobel Prize finally in 2013. So during last 20 years, again, the field of high energy physics has bagged 6 Nobel Prizes, not a joke. And on red, I try to highlight the ones related to neutrino physics. in the experimental on the experimental aspects. Like in 2015, the latest was Takaki Kajita and Arthur McDonald for the discovery of neutrino oscillations. You know all about it. In 2002, it was Raymond Davis and Koshiba. Sorry. In 2008, 2004, 1999, there were theoretical works which were highlighted. And today we will be talking about the prize in 2013, which was given to Francois Euler and Peter W. Higgs. So these were the two people who went to Stockholm, but actually there should have been many more. Unfortunately, you will see that one of the people whom we think that he should have also got the prize, he passed away, but there were few more in the teams. But the Nobel Committee, of course, they have their own considerations. So what was the citation of the prize? It says for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles and which recently was confirmed through the discovery of the predicted fundamental particle by the ATLAS and CMS experiments at CERN's Large Hadron Collider. So it sort of explains what exactly happened, that there was a discovery of a particle and it confirmed the theoretical idea. So they were naturally given the prize. And it was waited for almost 5 decades. This discovery was waited. So if we go back 5 decades, it happened that in 1964, within few months, there were 3 papers written by a total of 6 people. You can see the paper. I am not very sure you can see them properly. So this was Engler and Brout, then Higgs alone, and there were a team of 3 people, Guralnik, Hagen, and Kibble. So they wrote papers between, they published papers between June 1964 to October 1964. And here you see a group photo. Can you see it properly? Maybe I'm sure. Here you see a group photo where Higgs is missing. So he never met the other collaborators, at least the rest of the 5 people had some occasion to be together. And if you see here, people are writing in a team of 1, 2, 3 people. And the discovery paper, if you see for the Atlas and CMS collaborations, they have almost 5,000 authors in each. And from India, we had about 100 in the CMS collaboration paper. So history was in the making at CERN on 4th July 2012. So I think some of you might have seen this blue picture at the center, which shows the reconstructed event in a proton-proton collision where a candidate Higgs event is supposed to be produced. Higgs particle is supposed to be produced and it decays to 2 photons. And the energy of the photon is proportional to these 2 green streaks. And what are these other yellow streaks? These are the charged particles, mostly pions, which are produced when the protons are collided along with the Higgs. So, and this blue volume refers to mainly the central region of the detector. So this is just a computer reconstruction for the ease of visualization. So what happened is in the data, we tried to find out the kinematics of the events. And then we found that there was a smoothly falling distribution. I'll come to this M gamma gamma distribution later. And there is a slight bump with good significance. I'm not getting into the details of the how much was the significance, but this refers to the resonance. On the other side, in some other events, I have not given the picture here, when we looked into the 4 leptons, energetic leptons, electrons and muons, either 4 electrons, 4 muons, or 2 electron and 2 muons, and each pair, the charge sum is 0. And we expected the blue curves had there been no Higgs. And then it showed the data follows the blue curves, of course, and then around 125 in the region, we have to introduce this red resonance structure. Then only we can see that the data and the curves are matching. The theoretical idea is matching. So both these plots conclusively establish that yes, we are seeing a new particle which has decayed maybe to 2 photons or maybe to 4 leptons, and its mass reconstructed from these daughter particles is about 125 GB. On the left hand side, you will see two people. The lady was the spokesperson of Atlas experiment at that time, and this man was the spokesperson of the CMS experiment. They presented to the packed audience at CERN their results from the independent discovery results, and they are really appreciating. And subsequently, the current director of that time, the director Rolf Fair, and the previous directors, 4, 5 of them, they are all enjoying, and they are just everybody is in jubilant mode. So basically, this is the resonance. There is a continuum background, and there is a sharp peak with certain width, and so on and so forth. By the way, this width is not the natural width of the Higgs particle. Higgs particle, when the mass is about 125 GeV, its width is only 5 MeV, you can say, less than 5 MeV. But this width refers to our experimental resolution, which is about roughly say 1 to 2 GeV. So basically, we really hit a big step towards the understanding about the fundamental particles and their interactions. This is a discovery of a new particle of new type, spin 0. If you know that, of course, the matter particles are all Fermat, spin half, and there are carriers. I'm coming to it. There is like photon, you can say that is integer spin, but spin 1. So this was the only particle of its kind, spin 0, that was discovered for the first time. And even before the start of the LHC machine in 2009 and consecutive years, the LHC is always in the eye of the media. And of course, there were a lot of, what should I say, lot of coverage on the media. And Elon Musk gave the first breakthrough prize in fundamental physics in 2012 when he constituted it to the leaders of the Atlas and CMS experiments. And you can see here the Economist described that a giant leap for science. So finding the Higgs boson. And this Google, back in 2008, when the LHC first started circulating proton beams, they came up with this logo. Okay, we go on to see why this discovery was important. So in 1960s, a mathematical description of the fundamental particles and their interactions were developed. We call it standard model of particle physics. It now actually deserves to be elevated to standard theory of particle physics. Anyway, it's a mathematical theory of great beauty and power, and it is capable of prediction as well. So these are really very powerful properties of the theory. So therefore, it sort of visualizes that there are force carriers, these are spin 1 bosons, which mediate between point-like matter particles, spin half Fermats. And the symmetry required that these carriers should be massless. And we are familiar with the photon. This is the carrier of the electromagnetic interaction, which is massless, and of course it has infinite range. But the carriers of weak interaction, the W and Z, they are massive. And we all know, of course, that weak interaction has very short range, and I do not want to get into the details. So is there a conflict? Yes. So it was interpreted that the corresponding symmetry is broken. Now, to circumvent this problem, that how we can use the similar mathematical construct as we have done for quantum electrodynamics to describe the electromagnetic interaction, when we try to do it for the weak interaction, we encountered this broken symmetry. And as a sort of solution to that, the idea was proposed that there should be a spin 0 boson as a relic of this symmetry breaking. So this prediction was, of course, prediction. It remained a prediction for a long time. But when the W and Z particles were discovered, and subsequently for the next 2 decades, their properties were understood very well, and the theory of the standard model of particle physics, it gained much more respect because the predictions were all matching the data. And so it turned out as if the one leg of the table is missing. So experimental discovery of this particle was essential to complete the picture of the standard model. But I must say that this discovery reminds several decades back one of the famous scientist, the Wigner, he commented this aspect of theoretical description of physical universe, that unreasonable effectiveness of mathematics in describing the physical universe. Very nicely telling the situation. So we try to give obeisance to the three people, Brout, Engler, and Higgs, instead of calling it Higgs boson, as it used to be called earlier. So this picture on the left actually sort of implies that how Higgs is playing the central role in providing the mass to all the fundamental particles. You can see the 6 types of quarks, the leptons, the force carriers, and also to itself. And how it gives mass, that's again a theoretical topic which I do not want to go into now. But as the right picture says, it shows that the mass in giga electron volt scale, starting from a power of 10 to the minus 12 for the electron neutrino type, to going almost 1 TeV, several hundred GeV for top quark, the heaviest particle we know today. So how it does that, depending on the coupling, how this particular particle, electron versus top quark, interacts with the Higgs field, all pervading Higgs field, the mass will be decided by that. Mind you, these mass values are all experimentally determined quantities. Once, it's like the, you can say, gravitational interaction. You have to give the mass, and then you can find the gravitational potential, G m1 m2 by r, let's say. So similarly, you have to, in the theory, you have to give the charge of the particle, mass of the particle, etc., etc. That's in the standard model, that's how it works. But the interaction, how it will work, those are predicted by the theory. Anyway, so we were missing till 2012 this black spot, the Higgs particle. And once it was discovered, we now know that the particles involved in the standard model, they are all now, this is complete, the picture is complete. So actually, if we go back a bit, we see that though we said, okay, we are celebrating 10 years of LHC, it took 2 decades of preparation. It happened in the previous generation of collider called Large Electron Positron Collider at CERN during 1989 and 2000. It conclusively determined the number of light neutrinos having weak interaction to be 3. And this is a famous picture, most probably all of you have seen. So confirmation of the weak boson properties at lab intensified the serious search for the BEH boson. And so it sort of made sure that Higgs must be there. And if we do not find the Higgs particle, it will be really embarrassing for the theory, which is otherwise doing so well. And this is under the right side also gives another famous result from Leb, which sort of said that the Higgs particle should be more massive than 114 GeV. So it turns out that I did my PhD in the lab participating in the L3 experiment at lab. But anyway, this lab accelerator was dismantled, and now the same tunnel hosts the LHC accelerator. So what was the reason for the LHC accelerator? It was around 80s, early 80s, when the LEP accelerator was yet to come to life. It was decided that in future, it can also host a hadron collider. So this is what we call Large Hadron Collider at CERN. So it was discovery driven as well as exploratory machine with mandate to unravel the physics beyond standard model. Why discovery driven? Because it, from theory and experiments with the various considerations, it was realized that if Higgs ever existed in nature, its mass should be below 750 GeV, and the direct searches at lab concluded that its mass should be above 114 GeV. And why exploratory? Because LHC provided us the window to sort of test the physical laws at TeV energy scale, which was inaccessible till that time. So the idea was that we must find out the Higgs hunting over the complete allowed mass range of Standard Model. So from 100 to say 700 GeV. If the Higgs has to exist, it must be within this mass range. Otherwise, the Higgs cannot be the particle as a relic of the electric symmetry breaking we referred to earlier. And now, of course, we know that the LHC machine has not failed us. Within a short while, like a sprint in sports, we have discovered the BH boson, and we know its mass is about 125 GeV. And I think it really underlines the triumph of human intellect. Of course, we had to wait for 50 years, but we have it now. At the same time, we are yet to find any hint about existence of the physics beyond Standard Model, which we do believe that yes, it does exist, but we may have to be more smart and we may have to wait for a long time to really get any idea is that what type of physics is actually at play at the TeV energy scale. So now this long-term LHC project is a facility for exhaustive exploration of the TeV energy scale physics. Mind you, the science program also includes using the Higgs particle as a tool for thorough study of effects beyond Standard Model, which should be evident in precise measurements. So we have got the Higgs particle, we have been testing standard predictions of Standard Model, and even discovering the Higgs particle does not stop us in expecting that we will have physics beyond Standard Model. And on top of it, we can use the Higgs particle itself as a tool by measuring the properties of the Standard Model, as properties of the Higgs particle as predicted by the Standard Model very precisely. So basically, I come to the little bit of description about what happens at the LHC, or so for that matter in hadron collisions. As you know, that the fundamental particles as of today are the electrons and the quarks, etc. But quarks do not move around freely. So what we have in hand is the protons. So LHC is colliding two oppositely moving proton beams. And this is a cartoon here. So, and finally, when the protons are colliding, these constituents, so-called the partons, are actually free. And from two opposite sides, a pair of partons come forward and they interact. And out comes whatever the interaction has undergone. Basically, it is driven by the quantum mechanical probability. And for example, if two quarks, let's say a quark-antiquark pair from opposite side are colliding head-on with each other, it can interact mostly via strong interaction, let's say via exchange of a gluon. It can interact via electromagnetic interaction by exchange of by a photon. It can also interact via weak interaction by exchange of Z, if it is a neutral current interaction, if it is a, let's say, U and U bar quark. So many things can happen, and the couplings and the type of interaction that determines that at a given time what type of interaction it will happen. But it will, the interaction will happen at an energy which is only a fraction of the center of mass energy, let's say 13 TeV, at which the protons are colliding. So the total energy involved in the hard scattering varies, and potentially a variety of interactions can occur according to the probability of the interaction time. And we also know from the Einstein's equation that the available energy in the center of mass spin is suitable for momentarily producing an unstable heavy particle of mass m given by energy. And in case it happens, quite often we expect that the mass will show up the way we saw the Higgs resonance was. So this is what we expect, that if we try to measure the mass, the distribution from the kinematics of the event, and in case there is a particular particle at certain mass value, we will see the excess of events. So basically, to discover new particle, we need to have equivalent energy E in the center of mass system. So experiments at the energy frontier, what do they do? So we have been able to study the basic building blocks of matter at their interactions at a distance scale of 10 to the power minus 17 meter till now. Our next question is, do today's fundamental particles, the electrons, quarks, they have substructure or not? Now to answer this, we have to observe a substructure occurring at a length scale lambda c. And we need a probe of momentum greater than h cut by lambda. Since the resolution increases with energy, as you can see here, that momentum is greater than h by lambda. So the high energy accelerators are needed to get high energy beams. So at LHC, we have energy of 13 TeV at center of mass system. Mind you, 1 TeV is about 10 to the power 12 electron volt, and it is capable of probing length scale up to 10 to the power minus 18 meter. And LHC, as you may already know, that it's also called the Big Bang machine, since it allows to test the physical laws describing epoch of about, say, 1 picosecond after the Big Bang. So how do we access high energy in the laboratory? Let's say we are colliding two protons at LHC with, or let's say two different particles with different momentum. So invariant center of mass energy will be given by the 4 momentum square. And we refer it as root over square root of s given by E1 plus E2 square plus P1 plus P2, the vectorial sum square. Sorry, it should be minus. I'm sorry. E1 plus E2 square minus P1 plus P2 square. It is a minus. So in fixed target collision, what happens? That there is only one beam which is incident on a stationary target. So if we work out that if we have a accelerator where 6,500 GeV protons are hitting another proton at rest, then the available energy for actual reaction is 1140 GeV. On the other side, if we collide protons moving in opposite directions, then we will get 13,000 GeV, the center of mass, in the center of mass system. And so you can see the effort needed to energize a particle, let's say here 6,500 GeV. Once it is same, then we can go for colliding beam mode where the available energy doubles up. In a fixed target, of course, the rest of the energy is gone for the recoil of the target. So how do we accelerate particles? Here is a simple picture for the linear accelerator, where you all know that at the accelerate charged particles involving radio frequency high voltage setup, where at exit from a given sector, the particle is attracted towards the next. And the energy gained by traversing each sector is given by delta E equal to QV. So for a linear accelerator of high energy, the physical size will be very, very long, because there is a technological limitation about the field gradient that can be achieved in the laboratory. And already we have some accelerators which are several kilometers long. So, but it turns out that if we can manage to turn the particles again and again in a circular ring, we may be able to do a better job. So we use the same setup repeatedly to accelerate charged particles using the high voltage. And we bend the path using magnets. Essentially that is the case, and this is a cartoon of that. So we need high power magnets with the fields. Let's say we have a fixed tunnel of certain radius, accelerator of certain physical size, and the beam energy, beam momentum P is given through this relation. So now you see we have this Bremsstrahlung radiation problem. So the synchrotron radiation, the radiated power goes as fourth power of energy. So if we keep on increasing the energy, the most of it will be radiated out. And also you can see that since it is inversely proportional to the fourth power of the mass, putting a very high energy electron in a circular path, the radiation will be much more. And for proton, it will be less, because proton is 2000 times heavier than the electron. Anyway, so those are the basic ideas about how we get high energy in the laboratory. I come to the aerial picture of the Large Hadron Collider. Actually, these circles, white gray circles as noted here, it's just a cartoon on the physical aerial view. This tunnel is actually 100 to 150 meters underground. It really operates at the cutting edge of technology. It can collide protons or heavy ions. And Atlas and CMS, you can see here, they are in the diametrically opposite. In this picture, you cannot really, you can make out from this way. They are positioned in diametrically opposite parts of the accelerator, where the protons are colliding. And they were the two detectors, two major multipurpose experiments at LHC, which discovered the boson in 2012. So Indian groups participate in CMS experiment. So now I cheated you when I said 1 decade of LHC over. Actually, it was conceived in early 1980s. Design study took place in 1984 and it was approved in 1994. So India was actually one of the first countries to commit support for LHC construction. That is thanks to our great scientists with good vision. So India came forward. So start of the LHC construction was in 1998 and finally the first beam came in 2008. Finally, the collisions took place in November 2009. High energy collision started in 2010 at a center of mass energy of 7 keV. And by the time the Higgs discovery took place, protons were 4000 GeV was the beam energy and the center of mass energy was 80. And this machine is going to operate for 2 more decades. And of course, in a slightly more aggressive avatar, we will come to it. So this is a picture which shows part of the complex components of the accelerator. Actually, it's much more complex. So there are almost 10,000 magnets. Dipoles operate at less than 2 degree Kelvin. There are these radio frequency cavities per beam. There are 8 of them, so total 16 of them. These are really high tech. And protons turn more than 11,000 times per second in this tunnel. You can all find out much more mind-boggling numbers about the LHC. So what happens at the LHC? You can see this is a cartoon. So there are bunches. There are almost 2,800 bunches moving in opposite direction into upper beams. And when the protons are colliding, actually we are basically seeing the head-on collision of the constituents, as I already explained. So once in a while, there will be maybe a heavy particle produced and then it immediately decays. These particles we can't really observe or detect at all. And maybe sometimes we expect like Higgs particles are produced. It can decay to again another pair of unstable particles, Z particle, and then the Z decays only say 3% of the time to electron-positron pair, and we are able to catch these electron-positron pairs. If you remember the discovery picture, so from there we measure the kinematics of these final state particles, these electron and positrons, and then we try to do like work of a detective. So we know from our simulation studies what type of kinematics to expect, and then we try to go back and try to find the, say for example, the invariant mass of these 4 leptons. The one pair of electron positron here and another pair of electron positron here. So if we reconstruct the invariant mass of the 4 leptons, we should be, if there were no Higgs produced, we shall be seeing a smoothly falling spectrum. But since the mass of the Higgs is 125 GeV, we already saw there was a peak at 125 GeV. But to get to that, look at the situation. The selection is only 1 in 10 to the power 13 events. And these are quantum mechanical events. So we do not know which one. So we have to check all of them, all the events. So enormous computing resources, of course, are needed. And that's why the moment the LHC started, some of the people were teasing me that where is your Higgs, where is your Higgs? But truly speaking, within a short while of 1 to 2 years, we got the Higgs particle. But you can take that for an analysis to complete, it takes 2 to 3 years. So in the aftermath of the collision, you can have quarks produced, leptons produced. Quarks, of course, will be detected as hadronic jets. And leptons, sometimes if it is coming from the decay of W and the Z boson, the leptons will be sort of singleton. it will not be surrounded by many other particles. Whereas if bottom quark is produced and it decays semi-electronically, then such electron will be surrounded by other particles, other hadrons, for example. So here is a view on the right side of the, in the transverse plane, so-called R phi plane, where you can see how the events are reconstructed. I don't expect you to see things, but you can see here, typically, we try to find out what are the particles produced, what is the energy, in which direction it has gone, which part of the detector the particles have traversed, and so on and so forth. And again, on the bottom side, you see another picture where you see the maybe a larger portion of the detector where there are two muons, and because of the bending power of the magnet, the two muons paths are bent. We will come to it later again. So the total number of electronic channels in CMS detector or Atlas detector is roughly about 10 to the power 8. They are ready to take data. Every 25 nanosecond, the front-end electronics is ready. Proton-proton interaction rate is 10 to the power 9 per second, and the average event size is about 2 megabytes. Now, as I already mentioned, that when the protons are colliding, what type of interaction it will happen, it depends on the physics. So the event rate dNdt is given by cross-section times instantaneous luminosity. For example, at 8 TeV when the Higgs was discovered, so the instantaneous luminosity is 10 to the power 34 per centimeter square per second. It sort of gives us the idea about the flux. And then you can see the total inelastic cross-section is 10 to the power 9 per second, whereas the Higgs is produced 0.2 per second. This is the Higgs production rate. But we do not know which one, and all other particles or various other processes listed here, they are occurring at a much, much larger rate. So to really get a handful of Higgs events, one needs to wait for a long time because the rate is so small. So if we have high luminosity, then you can imagine from this, totally basically we want high integrated luminosity, that integral LDT. So we can have a statistically significant result if we have good integrated luminosity. And of course, extensive data mining in a concerted fashion is essential. The simulation studies are integral part of the analysis, but finally, we try to get the idea about the physical process or what all is happening mostly from the data itself, because our ideas or the implementation in the simulation is always limited. It's not perfect. And as you can imagine, machine learning in high energy physics is really a necessity. It is not a new phenomenon. I go to the next slide and I show you that from astrophysics I have coined this word called multi-messenger tool at LHC. So basically, we talked about Higgs particle, W, Z, etc. They are of the order of 100 times, let's say, heavier than proton. Their lifetime is of the order of 10 to the power minus 23 seconds, etc. Really unimaginable. They can decay to even further unstable particles. And finally, by the time the particles are detected and measured in the detector, there are only very handful, and they are same for independent of whether there is a top quark produced or Higgs produced or Z particle, etc. etc. So how we detect? We detect essentially via their electromagnetic interaction, sometimes via strong interaction. These are the two types of interaction we use, and we put suitable material along the path of these particles and try to find their signature. So you can see it's a slice of the CMS detector. It's like an onion shell actually. This is a very small slice cone you can think about. So the silicon detectors nearest to the interaction point, it can identify the passage of a charged particle. Say for example, the electron, the green path. And because the whole detector is immersed in a magnetic volume, so the path is bent. And then the yellow patch refers to the electromagnetic calorimeter, where the electron is made to lose its energy. It's a destructive measurement, and the electron completely loses its energy and produces signal via electromagnetic interaction. Mind you, Such a signal we can also get in the electromagnetic calorimeter due to the interaction of a photon of similar energy. What is the difference then? In case of photon, you see here that the green streak is dashed. That means in the silicon detector, it has not produced any signal. So similarly, you can see the other particles. The blue streak refers to the passage of muon. It does not lose much of its energy while traversing the detector material. In case of neutron, again the same. I'm sorry, I think you cannot see much. I cannot see much as well. The electron and photon are in the pista shade, and the neutron and proton are in the yellow patch. So from there we can, by putting different, it's like from the pug mark. You go to the forest and you try to find out the type of the pug mark, and you say whether it's a hyena or a tiger or whatever. So that's how you try to identify the muon, electron, photon, charged hadron, or the neutral hadrons, etc. So the main strategy of designing the detectors is that collide protons at high frequency, record as many collisions as possible using online selection trigger. We cannot really record all the events. And then we try to cover up 4 pi geometry around the interaction point, because we do not want to miss any of the particles that is coming out of the interaction point, because then we shall not be able to interpret what exactly happened. And we try to measure the position and the energy momentum of the particles as they traverse the detector with very high resolution. For example, in case of tracking detectors, you can see that the resolution worsens as the momentum of the particle increases. And we can try to have better resolution by putting stronger and stronger magnetic field and the lever arm, and making the lever arm L bigger and bigger. But of course, there are limitations, other limitations always. But anyway, this is how the resolution goes. And for calorimetric measurements, you can see here the dependence. It goes by inverse of square root of energy. And so with very high energy, you are left with this constant term B. So keeping these ideas in mind, we try to design the detectors. As I said already, the resolution of energy, momentum, as well as the position is of importance. So here I try to give, say, for example, tracker or the pixel detectors, which are nearest to the interaction point. At 2 centimeter, we can get 5 millirad the resolution. And the units, that the cell of the pixel, the dimension should be 10 micron. Whereas for calorimeter, which is a bit far away from the interaction point, by getting 2 cent at a distance of 2 centimeter, we can get resolution of 10 millirad. So this is a picture of our CMS detector, which is the compacted form of compact muon solenoid detector. It is very heavy, 14,000 tons. The diameter is 15 meter, length is 25 meter. It's really huge, huge detector. And in front of it, when we stand, we really at an awe, and it really humbles us. And it's such a complex detector. We know very little. Myself, I know very little about it, though I am, you can say, just an end user of what it produces, what it gives us. So here you can see that starting with we just a little bit talked about the silicon tracker. It's the largest silicon tracker ever built. Then we have the electromagnetic calorimeter, then followed by the hadron calorimeter. And in India, we built parts of this hadron calorimeter also. It is then surrounded by, afterwards in the outermost system is the muon system, which employs different types of detectors, including RPC, drift tube, and cathode strip chamber, nowadays also GEM detectors. So it is designed, built, operated, maintained, and periodically improved by the international community, including ourselves from India and undisclosed location. So right now there is some consolidation work going on, because the LHC is not providing proton-proton collision. So can you see a person? He is standing on a cherry picker, several meters above the ground, and trying to fix up some electronics. And you can see here near the center, it's there are some steel covers. Can you see here? Big one. Actually, here are the detectors which were built at TIFR and Punjab University, the hadron outer calorimeter, where all of us were involved. And there are so many complexities, it's not really showing up here. So I go to the next page. So discovery potentials basically drive the detector design. And I want to give you example what happens in case of electromagnetic calorimeter in CRS. You remember the short, small bump, the excess of events we saw when we found the Higgs particle. So we looked into the two photons, highly energetic photons, and we measured their kinematics. We made the invariant mass and saw this excess. And these photons are really, they can come due to all other, many other processes where the Higgs is not involved. And that is what we call background, and it has a falling shape. So mind you, this 6 decay to 2 photon, it has a very small branching ratio. But due to various considerations, it was realized that this is a discovery mode, and every effort was made to detect these photons and measure their kinematics very well. How was it measured? We used so-called these crystal calorimeters. Here is a picture you can see here. So let me just say that previous experiments, of course, had sort of hinted that most likely the Higgs mass range will be between, Higgs has to lie between 114 to 250 G. And in this region, the Higgs natural width is very small. So we cannot really have a very lousy detector. We have to have a detector with as good resolution as possible.
Kajari,
And yes,
I'm sorry. Can you take some water?
yeah, maybe. Can you give me some water? Water. Yeah. So excellent energy and position resolution was necessary, because you can see here that invariant mass is being constructed in terms of the two energy from the photons and the angle between the two photons, the cos theta. So the detectors must cover, as I already said, it's the interaction point region. It's highly granular. So all that required that almost 80,000 lead tungsten crystals were put in. They are of length 23 centimeter, and you have already seen the picture. So you make sure that the photons lose all of their energy. But the front face is as small as 2 centimeter square, and the back face is about 3 centimeter square. So, and that's why to cover up the whole region, we needed about 80,000 crystals. And lot of R&Ds has gone into finally making this detector work, choosing the material, how it will work, etc., etc. And some of the work was also done, including simulation and radiation hardness studies in BRC, including the irradiation facilities. We did it in India. That was in early 90s. So as you can imagine, with such a large number of crystals for only for the electromagnetic calorimeter, the total number of electronics channel is really very, very large. Of course, the main contributor here is the silicon tracking detector. And the amount of data which will come out of it is very, very large. So per year, per experiment, we are recording almost 10 petabytes of data. So how to analyze this? So as a natural evolution from World Wide Web, WWW, the internet-based worldwide distributed computing grid was sort of developed, and this WLCG resource is now equivalent to about 10 million cores. And the idea is that at any time, I can have access to any data. I, in the sense the collaborator, the scientist, can have data sitting anywhere. And that is happening for last 10 years. So we share more than information, computing power, monitoring, etc. But the key to this is that the large area network speed is comparable now to the speed of the compute processors. So that's how it works. The data may be sitting somewhere else in the world, and my computer also may not be utilized to process the data to produce the results I'm interested in. That's how it works. And we also have a grid tier 2 center at TIFR. We also have a cloud-based facility which can be put into effect whenever necessary. So by doing all this, we know that Higgs physics, though it started only recently, it has matured quite well, in the sense that we are able to characterize this resonance in terms of measuring this mass, the width, the spin, how it couples to WZ. Remember what I mentioned earlier, that all these particles interacts differently. Now, if you take an electron and a muon, how they interact with the photon, you know they interact almost the same way as long as the charge is same. But in this case, each of these particles has different strength of their interaction, so their masses are different. And the theoretical idea says that suggested how they should be, and they all match as well with the measurements. That's right plot shows that. Numerical other measurements also sort of confirm that yes, the way standard model has envisaged the properties of this boson, the data sort of is compatible with that. But still, there is insufficient statistics, one can say. The data still has some leeway, there are some errors. So within errors, we can still say that no, it may be a Higgs particle of a different structure, or there may be we are seeing some effects of new physics. So that's why we have to keep on doing better and better measurements. And to do that, we need large statistics data. And finally, we can say that, okay, this is the Higgs particle as envisaged in the standard model. In parallel to doing Higgs physics, of course, LHC experiments have been very extensively involved in searching for the physics beyond standard model. I mentioned here only one case. Say, for example, we expected that there may be, let's say, like the neutral Z particle, there may be some other particle, heavy particle, let's say few TeV, few thousand GeV. Remember, Higgs is about, the Z particle is about 90 GeV. But since the LHC is able to provide us enough energy in the laboratory system, one can imagine that few TeV particle can be produced momentarily, and it can decay as well to hadronically. And let's say if it decays to jets, sometimes these jets could be very fat jet, but within that jet there may be substructure. So what happens is that, for example, let's say this particle X can decay to two Z particles. These two Z particles can decay to two quarks, each of them. And from these two quarks, we can expect jets. So finally, you can see here four jets, but two jets are actually forming a fat jet. So by measuring such things, one can see that again we look for a falling background. Of course, we have falling distribution from the background, but we can try to find out if there is an excess of event, and we don't find anything. So that's why we exclude that yes, there is no new resonance of mass up to almost 8 TeV. So this is one of the example where we have been searching that if there are new particles as envisaged in various theoretical constructs beyond standard to describe beyond standard model physics. Another important issue is the dark matter. You all know that, of course, the dark matter is there and it is just waiting to be found. So the trouble is that we do not know what is the mass scale involved in the dark matter. It's, of course, very weakly interacting, and so it is very difficult to find out the presence of dark matter. But let's see, one can imagine that dark matter may be produced, and we have to find out how we can interpret our data, assuming that, okay, a dark matter of certain mass has been produced. And if we try to do that, we see that, again, we have not seen so-called signatures of a dark matter. So what happens in dark matter is like the neutrinos you are all familiar with. In case we have a dark matter produced, it carries away energy momentum, but it does not, we cannot detect it in the detector. So it will produce so-called transverse missing transverse momentum. Because in the parallel direction, if you remember, though we know the kinematics of the protons are moving along z direction, so there is no transverse momentum in the transverse direction. The longitudinal direction is the beam direction, the z direction. So in the final state also, we should not have any momentum. So transverse momentum in the final state also should be 0. So in case there are particles, let's say heavier cousins of neutrinos, here we call them as chi, then they have carried momentum. So if we measure all the transverse momentum of all the visible particles and we sum up, we will see that the sum is not coming to be 0. So from there, we can interpret, yes, we have a missing transverse momentum, and maybe that is carried by dark matter particles. By doing all this, we try to see that these LHC experiments are sensitive to detect such particles if the particle of such are below, say, 10 GeV. There are non-accelerator based experiments which are able to detect much better such dark matter particles if the mass is above, say, 7-8 GeV. compared to the CMS or Atlas detector. So what happens in the future? So we can take a stock of the situation that numerous measurements at LHC have established that standard model is correct up to the energy scale of TeV, that is 10 times higher than the electroweak scale, that is the mass scale of W, Z, Higgs, etc. But the justification for existence of physics beyond standard model still holds. So now the best thing will be that, okay, we have a fantastic machine which is working very well. The experiments are also working very well, in fact, beyond expectation. So we should not give up. And in fact, we run the machine for longer time than originally planned. And we should run the machine much more aggressively by tuning the machine, tuning some of the parameters. We can achieve 10 times more luminosity, instantaneous luminosity. And the plan is to run the machine till almost 2040s. So right now, as I have mentioned already once, if you see this plot at the bottom, you can see here we have a name run 1, run 2, run 3, etc. These blue portions, the fat portions are called long shutdown 1, long shutdown 2, where the machine does not provide collisions for almost 2 years, where the machine is sort of consolidated or improved upon, as well as the detectors. And then it comes up with better performance. So now we are at, in 2020 we are in shutdown period, and in 2021 we will again start having collisions which will run for 3 years. Then again we will have shutdown, and then the machine components will be improved so much that it will be able to give us very high luminosity, and then that is the one we call it high HLLHC. And we are preparing, as you have seen here, to have a machine working from day one and the detectors able to collect data and analyze. A preparation of 10 years is necessary. So that's why the preparation for HLLHC has started. The time the LHC actually started, by 2010, people started thinking about high luminosity option. And that's how these long-term experiments run. And the results today we are having is sort of corresponds to the integrated luminosity of about 150 femto inverse, whereas by end of HLLHC, we may have 5,000 femtoid inverse. So you can imagine that if we have a very, very rare process, we shall be still able to catch it by running this LHC machine for a long time. So one of such example is what is called vector boson scattering process. So it is actually at the heart of the electroweak symmetry breaking. So here I have given you so-called the cartoon called the Feynman diagram of what happens, that let's say from the two protons, two quarks are coming on the way, W particles of same charge, W plus, are being emitted out by these two quarks. And in the final state, you can have these two quarks and the two Ws are there in the final state as well, and then they may decay either hadronically, but we shall be able to detect them only if the Ws are detecting maybe electronically. We shall be able to detect them better. So in the final state, we will have two Ws and two Zs due to these two quarks with certain topology. And look at the Feynman diagrams. There are various possibilities where I can have, starting from the same initial state, I can have the same final state. So theoretically, I have to consider all the possibilities. Now, if we say that, okay, the Higgs is not there, so we do not know how the Ws are became massive, so there is no electric symmetry breaking, etc., then the first diagram cannot be considered. But if we consider only the second and third diagram, then we see mathematically there is an inconsistency. So by measuring the cross section, we can establish that yes, the first diagram is essential, and that through so-called the Higgs mechanism, the electric symmetry breaking, the longitudinal components of the W bosons becoming massive, all that is actually involved, all that is will be evident if we measure the kinematics of these leptons very well and try to find out. But it is very, very difficult because the cross section is very low. But definitely going by the LHC culture, that what people at the beginning or the start of the LHC also, what people thought that we cannot do, we are able to do now. So we shall be able to measure the longitudinal components of the W boson, and that will sort of really establish that yes, that is where the Higgs is crucially playing the role. But of course, for this, we have to prepare well, including designing or improving upon our detectors. So when the LHC machine is coming up in a better way, our detectors also are being improved upon, or actually almost being some of the components of the detectors are being replaced. So in this picture, if you can see, I mentioned about two jets. These jets are going in the forward backward direction. But typically what we thought when we designed the LHC experiments is that we will see massive particles. And when you can imagine the massive particles, they will not move much in the very highly, like I showed that 8 TeV particle, let's say resonance particle, or 5 TeV. So it will not have too much longitudinal momentum. So it will be almost at rest, and the decay particles from such massive unstable particle will be mostly at a large angle with respect to the beam energy. But that means we were mainly concentrating in having the best detector components in the central region of the detector. But now to see such vector boson scattering or other processes, we also realized over the time that we must have the forward region also instrumented very well. And that sort of has dictated some of the detector designs for the upgrade of the detector, which will be online in 2027, meant for HLLHC. And ideally, I have already crossed my time limit quite a lot, so I do not want to discuss too much about the upgrade of the detector. So basically, it is also realized that silicon comes to our rescue. Silicon gives us very good position resolution, and also recent studies have also said we can get even timing information from silicon detectors. And so we try to use silicon detectors maximally. We improve upon our detector techniques, how we detect, and the electronics very well, so that we are ready by 2027. Some of the R&Ds are going on in full force, even in India also. And finally, the production of these detector components will take place, say, for example, after 3-4 years. It will take 5 years, and then we will install, and then the machine will come online, and we will be able to do a lot more physics for next 10 years. So I talked about preparing for the machine, preparing the detector, the improving. So all that also needs really some space, because these 10 years, when before the HLLEC comes up, the current LEC machine will continue to provide us data, and we have to do the experiment. So we cannot disturb the current experiment. So additional space is being, experimental hall is being created. So here you see a picture that digging work is going on. Now, I told you that LHC is going to live till 2040. So is it the end of the energy physics? At least for collider physics? No. Lot of effort is also going on to have different types of other machines to have access to higher and higher energy. So there are some proposals. We have not yet heard the decision of the wise people, which are expected sometimes maybe this year, where we can have a future circular collider at CERN, and this will be 100 TeV. LHC currently is colliding protons at, let's say, 13, 14 TeV, but we are talking about 100 TeV now. It will be in 60s or 70s. And it will also need stronger magnets, dipole magnets. So again, R&D is going on. There is other possibility in Japan. There may be linear collider, or there may be a circular collider in China. But all these are at the proposal level. Now, COVID-19, we are all keeping the fingers crossed how the whole world will evolve. The humankind has to take proper decision, how to live, how to do science. So let's not spend any more time about it. So I come to the summary. So I hope I have been able to convince you that LHC project is really fantastic in every sense. It is, I think it's an unbelievable pursuit for the unimaginable. It is the largest scientific endeavor ever taken up by the humankind. It involves almost 10,000 people, and it's a fantastic, what should I say, benchmark, or you can say model for scientific collaboration. And its scientific goals are well defined, with far-reaching consequences on our fundamental knowledge about the genetic code of the universe. That's about the Higgs particle we discussed today. So you can say, okay, you have discussed already, in 10 years have passed and you have discovered only one new particle. Fine, but that's a big deal, because the detailed studies of its properties are slated to enrich us with deeper understanding about the building blocks of matter and their fundamental interactions. And coming years, of course, we'll see many more explorations for physics beyond standard model with an improved detector for a more aggressive machine, HLLC. So it may be a marathon. It may not be sprint. But we will not lose hope, and we will continue with even more fervor and enthusiasm to work for the LHC. So LHC era has also seen prodigious developments on the theoretical side. Truly speaking, without that, we could not do what we have learned about Higgs physics, about in general the physics of the collisions that is taking place at LHC. So next 2 decades will be intensive with analysis of collected data and preparation for future operation of LHC. That is the job for the experimentalist. I just tried to flash little bit about what we do for the society. Now, on short-term basis, you cannot really say, okay, this is a blue sky research. What is the application? Of course, we know that World Wide Web was invented to have access to only information, access to information, mind you. That was in 1990s. Initially, it was not appreciated, but now we know that what it means to all of us. Similarly, many today, if you go to a hospital, for example, say, you will see the instruments all are based on physics. And here I try to list some of the applications which have come out of the accelerator-based research, fundamental research. So synchrotron light source producing high energy X-rays, material science research, protein modeling, controlling power plant gas emission to superconducting accelerators in hospitals, hadron therapy, positron emission tomography, and implantation of electronics, and the list goes on and on. Many of the things even you know in the context of as well. So I think it has time has come for me to stop. So thank you for your attention. And I thank again Dr. Satya for giving me a chance to talk to you about LHC. Thank you.
Thank you very much, Kajari. That was really indeed an excellent lecture. You covered a vast material, gave in the process almost 35, 40 years of history of LHC, the instrument building, the accelerator building, all the fundamentals of both accelerator side and as you rightly pointed out, the outstanding detectors and challenges, both in terms of detectors and instrumentation.
Thank you.
And
Thank you for the kind words.
it was really great that you also brought to also towards the end what lies in the area of high energy physics in the future, and touched upon both FCC and other LC linear collider detectors. And your last slide was something indeed very satisfying to also say that all that is happening is not just by few thousand physicists enjoying their liking for physics,
Yeah,
also how it actually is helping the people on the street, and particularly the medical field
yeah.
in particular. So it's thank you really very much for covering this vast material in about 1 hour. So I hope
Thank you.
we have some questions from the participants. So may I request the people who have questions to raise their hand. I'll come to you and
Shall I stop sharing the slide?
yeah, you can, yeah, sure.
I can again get back, of course.
Okay. Yeah, so we have one question from Shailesh, so I'm going to unmute. Yeah, please
Hello.
go ahead, sir. Yeah.
Yeah, my question is, LHC is like a long ring experiment, 27-kilometer long, but the linear colliders are mostly only 2 or 3 kilometers long. So, is that is it because of some logistic problems or some like land acquisition problem, or are there other
No,
scientific challenges
no,
as
not
well?
really. Depends on what type of energy you are looking for and the gradient of field. So that's why the R&D, the technology for the accelerators are really has to be very extensive. As I mentioned earlier about the field gradient, if you can achieve very high field gradient within a short length, you can energize the particle much higher scale.
Yeah,
Okay.
but like LHC, the energy at LHC is around 14 TeV, which is not reachable at other linear colliders. So if we may increase the length, we may get the similar energy, and we will not have any kind of synchrotron radiations as well.
Yeah, but that will be really a bit too much to have such a long accelerator to get the
Okay.
same 14 TeV.
Okay.
So
Thank you.
you develop here the dipoles
Yeah.
to energize the particles, and you also develop these superconducting radio frequency cavities to sort of replenish and make the particles, then the particles bend around and then pass through the same tunnel. But in linear collider, you have to have really very, very long, of course. But it will be
Uh,
a lot more R&D needed to have, let's say, 100 TeV, what people are talking about, to have a manageable length of the accelerator, linear accelerator. To get 100 TeV proton beam, I think it will be really too long to have a linear accelerator.
okay.
Okay.
And I have another question.
Yeah, please
Uh,
go ahead.
yeah, the electromagnetic calorimeter was comparatively smaller in size than the hadron calorimeter. So is it like most of the charged particles will lose their energy in that electromagnetic calorimeter, and hence we may be able to detect them?
No, typically you can say that the loss of the energy goes as logarithmic power, how it goes, but it depends on the material. So that's why a lot of R&D goes in choosing the material of the electromagnetic calculator. If you go to the nuclear physics lab, what you see? You see sodium iodide, you see barium fluoride. Then you try to find out a dense material, okay, very dense material, so that high Z material makes the probability for electromagnetic interaction high. So that's how, say, for example, if there is a photon incident, and then it will come to the nucleus of the material, and then it will create a electron-positron pair. So if it is a low Z material, the photon will not make a pair. So that means it is able to traverse a longer distance within the material. So that's why if you have a high Z dense material, then the photon will lose its energy faster. And for that's how this cerium lead tungstate material was chosen, along with other properties I had mentioned briefly. And so it is dense. The whole idea was that, as the name suggests, the compact muon solenoid. So the magnet size sort of dictated what should be the depth of the calorimeter within the magnetic volume. So knowing that we have to detect the Higgs and in certain certain energies of the decay products, it was realized that okay, electromagnetic calorimeter has to be of this type. And then when it comes to hadronic interaction to make the hadronic calorimeter, again we try to go for high atomic number. And there are it's not a what it is called homogeneous calorimeter, like in the case of electromagnetic calorimeter, it's a bulk excitation. Okay, the whole crystal is excited when a photon is passing through it. But in case of hadronic calorimeter, it's a sort of a sandwich between sensitive volume and sort of interaction volume. So you make the particles lose energy by repeated interaction in a dense material again. And in the next layer, you put a sensitive detector, and there you try to measure the energy of the particles produced. And from there, you try to interpret. So truly speaking, the depth of the calorimeter, which is lying within the solenoid magnet of the CMS, is not enough. And that's why this hadron outer calorimeter, which was made in India, it was put outside the magnetic volume. And there are other ways to take care of it. And that's how it has been happening.
Thank you very much.
Okay. Uh, Kajari, if I can ask
Yeah.
a question, maybe on behalf of others. So, of course, you did mention exhaustively about the Higgs search and also the results, and also what lies ahead. One of uh, the major agenda of the LHC program, apart from Higgs, is also, I think, is something the supersymmetry and other new phenomena. So, there is some kind of disappointment in some sense in the may not be people who are involving in, but also maybe people other So what do you think the prospect of this physics maybe coming up with a better results in the next phase, your run 3 and so on? And I mean, what is in general
Yeah, so what is
opinion of?
in general thought is that maybe we thought our life will be easy. We can see a supersymmetric partner of, let's say, quark, which is called squark or a gluino, being produced as a 2 TeV or 3 TeV, and then it decays, and we shall be able to detect the way we are detecting, let's say, Z particle decaying to two quarks in terms of jets, etc. But it can happen due to certain other properties that there may be a long-lived particle. Okay, it's a different form of physics beyond standard model. Maybe not the SUSI, the way the supersymmetry we thought about, the way the structure is. It may be a different construct, mathematical construct, which will allow a particle to traverse the detector up to certain distance and then decay. So, and the one of the first question comes is that trigger. Okay, we shall be able to see that yes, when the protons collided, in the subprocess level, when the two partons interacted, the momentarily the energy density was very high, which is suitable for production of a massive particle. Okay, so that massive particle, of course, does not live long, and the decay products should carry enough energy and momentum. And we have till now designed our trigger saying that, okay, I expect to see a photon above, say, 10 GeV, 20 GeV, starting from the interaction point, which is roughly, let's say, geometrical center of the detector. But if a long-lived particle is decaying, let's say, for a lepton, or for an electron, at a point which is, let's say, 1 meter into the detector volume, then we do, till now we did not know how to trigger such events. So these are the developments which will come up, and there are always these supersymmetry or various scenarios, physics scenarios beyond standard model. They try to tune various parameters through which they say that yes, maybe we shall be able to see the particles who are not like quarks or gluons, the squarks and gluinos so-called, but maybe like neutrinos. Like, say, for example, what we call charginos and neutralinos, that their interaction cross-section, their production cross-section is much lower than the production cross-section of squarks and gluinos. So in that case, unless we have large amount of integrated luminosity, we shall not be able to get enough number of such events where charginos and neutralinos are produced. And then after detecting them, we shall be able to say more definitively that whether supersymmetric theories are really a failure.
On the foreign comment. Yeah, we have two quick, two more questions. I hope we will finish fast. Yeah, Balasubramaniam, can you ask your question?
Hello, good evening, everyone.
Hello.
Ma'am, I have a request. I mean, could you please share your experience during the discovery of gauge bosons with the LEP and Higgs discovery at LHC? I mean, how was the excitement?
Yeah, yes, I am really lucky that, first of all, I'm really lucky to be living in an era where I could see birth of two accelerators. So LEP started taking data in 1989. I was a PhD student, and I was also lucky that I happened to be at CERN at that time. And I will tell you that these engineers who are really the lifeline for the success of such collider experiments. So the engineers, they really do fantastic job. And the LEP collider was being ready during 80s. So back in 1988, and they declared that we will start the LEP machine on the Bastille Day. So 4th July is the Bastille Day. So, and 1989 was the 200 years of Bastille Day. So these French engineers said that we will start the LEP machine on that day. And it happened to be a Saturday. I was working in there used to be the so-called computing room. I was working there. And one of the important scientists, a big professor in MIT, he came into the room around 3:30 in the afternoon, and he said that electron has made a chip inside the LEP accelerator, the LEP beam. And soon after that, after a few hours, the collision started. And you know, those days, internet, of course, was not there. So collision data was being recorded. And in the computing room at the experimental site, the data was being stored in really pooled, the disks. And these big disks have to be driven to the CERN computing center, where a lot of data messaging was there. Then we could see the properties of those events on the computer at CERN. So all this happened, and we were doing shifts. We were looking at the properties of the events, and we were trying to find out if we can see the Z being produced and decaying to various particles. So the first Z was detected around, say, for example, I think it was around 10 p.m. or 11 p.m. in the night. And we were all doing all the scanning of, so-called scanning of the events. So it was really very nice.
About the Higgs discovery, ma'am.
So about the Higgs discovery, of course, by that time, internet has come. And of course, at a given time, at CERN, there are several thousand people looking at the data, analyzing data, taking care of the detector, doing the online shifts. So we also do the shifts. But Higgs discovery is based on a data volume of, say, 2 to 3 years, 2010, 2011, and part of 2012 data. And we were continuously looking at the data, trying to find out how to beat the background. So the background is much, much larger. And in parallel, we were doing simulation to find out what will be the signature of a Higgs production and, say, decaying to 2 photons. Mind you, that Higgs mass was not known. So the small excess of events at 125 GeV, which was known, that was not known a priori. So all the mass windows had to be thoroughly searched. I don't know whether I am able to pass on the message across. So the photon properties had to be studied very well. But before we did that, we had to make sure that our electromagnetic calorimeter is working as it is expected, because the photons are detected in the electromagnetic calorimeter. So what we do is that what in astrophysics term it is called candle. So our candle for LHC is the Z particle, Z boson. So this Z boson decays to 2 electron-positron pair. Okay, and these electron-positron pair, we measure their kinematics in the same electromagnetic calorimeter, these crystals, and we also connect the streak of their path in the inner detector. I tried to explain to it in the tracking detector, the silicon detectors. So the difference of electron with respect to photon is that the photon will not have the tracks, but the electron will have the preceding track in front of the electromagnetic shower, so-called. So if we can say that, yes, we have been, and we know very well the Z particles properties, so we can know the kinematics of the electron coming out from the Z decay, so we can make that invariant mass. So by measuring the invariant mass of the 2 electron and positron, and seeing that, yes, there is a peak again above background at 91 GeV, which is again the Z mass was known in advance very well, we could say that, yes, our electromagnetic calorimeter is doing very well. If the invariant mass of the electron-positron pair coming from the Z particle, rather in conformation with the properties of the Z decay, were at, let's say, 93 GeV, whereas we know that the Z particle mass is 91 GeV, then we have to realize that there is something wrong in our electromagnetic calorimeter. So once we show the world, we showed the candle that, yes, we are able to measure the Z particle very well, then we can be confident that, yes, we can measure the Higgs going to 2 photon very well.
Okay. I'm going to go for one more question.
I was doing mostly that type of, you can say, validation.
Okay.
Because I was not sitting at CERN. You can imagine that people from all over the world, they managed to spend a lot of time and look at the data. And there is a lot of competition because these are high profile analysis. But behind that, a lot more analysis are needed. Like I told you that showing that Z particle doing this, getting into the electron positron, and you look at the invariant mass. But
Kajari,
all these forms the stepping stone for the discovery. Yes.
Kajari, I will take one last question.
Okay.
I think it's already 7:30. There is one Chaitanya Paranjape. Let me, yeah, can you please ask a question?
Why do we can you hear me?
Yes, yes, very much.
Why do we focus on proton-proton collision only, other than the reason protons are easy to produce? Is there any
Yeah,
specific reason?
yeah. First of all, sorry, am I?
Please go ahead, Kajari. You can
So
hear you.
basically, we needed to have enough energy in a controlled fashion in our laboratory. Okay. Agreed. So for that, we had to accelerate, and for acceleration, it has to be charged particle because we are depending on the acceleration in an electric field, and of course, it's a circular collider, so we put the magnets and so on and so forth. Now the question is, electrons are the fundamental particle. So if we put electron in a collider, we know from the beam energy what will be the center of mass energy, what will be the available energy to me. So in the large electron positron collider, we could tune the beam energy, and we sort of scanned around the Z resonance from 85 GeV to 105 GeV, where we saw that the peak is at 91 GeV, corresponding to the Z particle being produced. Now, in this case, as I told you, the main reason for the Higgs, for the LHC, was to find out if really Higgs is there. If it is there, its mass has to be between 114, let's say 100 to 700 GeV. So between 100 to 700 GeV, that means our accumulated energy density in the laboratory should have this big spectrum between 100 to 700 GeV. So you cannot have an electron machine and keep on tuning, because as we see that the mass values, if you remember the electron mass, the proton mass, they are not integers. They are not 105 GeV. Actually, Z mass is 91 point something something. W mass is 80 point something something. This is nature swims. So similarly, we do not know what is the Higgs mass. So we cannot really tune the beam energy of the electron and try to find out a mass of an unknown particle. So that is why it is called broadband machine. So hadron machines are broadband machine because when you are colliding high energy protons, it is the constituents, the quarks and gluons at such high energy, they are effectively act as free particles, and then they come into contact. So now in the beam, you are colliding protons, and these protons actually, mostly they are undergoing elastic collision. They are saying hi, hello, like on the road you go and meet people, you go in the station, you say hi, hello and go away. Once in a while you meet your friend, then you stop by and you interact and you do things. So or you can sometimes collide head on because you have not seen or you are looking at your phone. So what happens in that case, the impact, so-called the impact parameter, will be very small. If the impact parameter is small, that means the inelasticity of the collision is very large. That means the energy density produced in such collision is large. That means we have a possibility of producing momentarily an unstable particle of mass given by the energy transfer which has occurred between the two protons. Am I clear?
Yes.
Okay.
You get it? So the energy available in a hadron collision on an average is say 1/10 of the center of mass energy. So if we collide beams of 4 TeV protons, center of mass energy is 8 TeV, but effectively we are able to get interactions from few GeV to up to say several TeV. So that is why we could probe physics at TeV energy scale, and we could also scan the possible Higgs mass range up to 700 GeV.
I think
Okay.
we must give you rest. Your throat is really hurt. We could
Thank you.
feel sorry about that. But I mean, also once again, on behalf of all the participants, let me thank you for a really wonderful lecture. You covered a vast amount of material, and of course, it's a nice discussion. Maybe given the time, maybe 1 or 2 more questions would have come, but it's already past 7:35. You have been speaking for more than 1.5 hours.
Okay, if people have any pressing question or something which may help them in the talk, in
of course, they can also write to you. I mean, you're well known.
Okay.
So with that, let me thank you, and then
Thank you again, Dr. Satya.
okay.
It was really a pleasure to talk to you.
Okay, thank you very much. And for the benefit of participants, let me also
Thank you for your interest, all the audience.
okay. I just want to, before I close, I want to once again remind you that next week we have Professors Rajshekharan Rajaji and Poonam Mehta and Professor T.P. Singh speaking on 3, of course, different topics and equally interesting. So please come back and join at the same time at 6 p.m. So with that, let me close today's session and take care and stay safe, all of you. Bye-bye. Thank you very much.